Introduction. Sister, today I am going to perform an experiment which I had learnt yesterday in my school.
Great! I would like to see the experiment.
Yes, sure. We are going to measure the temperature of a liquid. We need just one flask of hot water and one thermometer. Firstly, we dip the thermometer into the glass. Then we measure the exact temperature of water.
Brother, how this thermometer works?
Listen, thermometer has mercury in it. When we put thermometer into hot water, then the heat from the water causes the expansion of the mercury. When mercury stops at a point, that point indicates the temperature of the water.
It is quite interesting and I want to know something more about it.
Students, today we will learn more about the thermal properties of matter. Objectives. At the end of this lesson, you will be able to define temperature and heat, measure temperature, analyze ideal gas equation and absolute temperature, calculate thermal expansion, evaluate specific heat capacity, define calorimetry, learn change of state, know about heat transfer, calculate thermal conductivity of a substance, define Newton's law of cooling. Temperature and heat. Temperature of a body is defined as degree of hotness or coldness of a body. Its SI unit is Kelvin and degree Celsius is a commonly used unit of temperature. Heat is a form of energy which gives us the sensation of warmth. Its SI unit is joule and other commonly used unit is calorie. 1 calorie is equal to 4.184 joule. Its dimensional formula is ml square T to the power minus. Measurement of temperature. A device used to measure the temperature of a body is called thermometer. Thermometer are designed on different scales are following: Celsius scale, Fahrenheit scale, Kelvin scale, and Ramer scale. Boiling point of water is known as upper fixed point. Freezing point of water is known as lower fixed point. Consider a body having temperature C on Celsius scale and F on Fahrenheit scale. Then C upon 100 is equal to F minus 32 upon 180. Example. Let's take an example on measurement of temperature. A newly designed thermometer has its lower fixed point and upper fixed point marked 5 degrees and 95 degrees respectively. Compute the temperature on this scale corresponding to 50 degrees Celsius. Let's see the solution. Let theta be the temperature on the scale corresponding to 50 degrees Celsius. Then theta minus 5 upon 95 minus 5 is equal to C upon 100. On simplifying, we get theta minus 5 upon 90 is equal to 50 upon 100. Hence, theta is equal to 50 degrees. Thus, the required temperature on the scale of the designed thermometer is 50 degrees. Ideal gas equation and absolute temperature. all gases at low densities exhibit same expansion behavior. Since PV is equal to constant and V upon T is equal to constant, then PV upon T is also constant. This relationship is known as ideal gas law. Ideal gas equation may be written as PV is equal to mu RT, where mu is equal to number of moles in a sample of gas and R is equal to universal gas constant. In constant volume gas thermometer, temperature is read in terms of pressure. The temperature at which all molecular activity except vibration ceases is known as absolute zero. It is a theoretical value derived by calculations and projections from experiments with the behavior of gases at extremely low temperatures. Absolute zero is estimated to be equal to minus 273 degrees Celsius. Thermal expansion. Thermal expansion is defined as the process in which a substance expands on heating. Thermal expansion is of following types. Number 1. Linear expansion. In this type of expansion, substance expands in one dimension only, that is, in length. Number 2. Areal expansion. In this type of expansion, substance expands in two dimensions, that is, in length and breadth. Number 3. Volumetric expansion. In this type of expansion, substance expands in three dimensions, that is, in length, breadth and height. Linear expansion. Consider a rod of length L, which is heated by a temperature delta T, and let its length become L dash. The change in length is directly proportional to the original length and change in temperature. It gives L dash minus L is directly proportional to L delta T, or L dash minus L is equal to alpha L delta T. Value of alpha is equal to L dash by L upon L delta T, where alpha is equal to coefficient of linear expansion. Coefficient of linear expansion of the material of a rod is defined as the change in its length per unit original length per unit rise or change in its temperature. Areal expansion. Consider a plane of original surface area A at temperature T1. Let the area of the plane be A dash at temperature T2. It gives A dash minus A is directly proportional to A delta T, or A dash minus A is equal to beta A delta T. Value of beta is equal to A dash minus A upon A delta T, where beta is equal to coefficient of areal expansion. Coefficient of areal expansion is defined as the change in the area of the body per unit original area per unit rise or change in its temperature. Volumetric expansion. Consider a spherical body of original volume V at temperature T1. Let the volume of the body at temperature T2 be V dash. It gives V dash minus V is directly proportional to V delta T, or V dash minus V is equal to gamma V delta T. Value of gamma is equal to V dash minus V upon V delta T, where gamma is equal to coefficient of volumetric expansion. Coefficient of volumetric expansion is defined as the change in volume of a body per unit original volume per degree rise or change in its temperature. Specific heat capacity. The specific heat of a substance is defined as the amount of heat required to raise the temperature of its unit mass by 1 degree Celsius. It is represented by C. Its SI unit is joule per kilogram per Kelvin. Its dimensional formula is m to the power 0, L squared, T to the power minus 2, K to the power minus 1. The amount of heat given to a substance of a mass m to increase its temperature by delta T is H is equal to mc delta T, where H is equal to amount of heat required and C is equal to specific heat of the body. Heat capacity of a body is defined as the amount of heat required to raise the temperature of the entire body by 1 degree Celsius. Its dimensional formula is ml square T to the power minus 2 K to the power minus 1. Its SI unit is Joule per Kelvin. Heat capacity is equal to mc, where C is equal to specific heat of the body and m is equal to mass of the body. Calorimeter. The method in which a quantity of heat either absorbed or given up by a body is measured is known as calorimeter. Heat loss or gain is equal to ms theta, where m is equal to mass, s is equal to specific heat of the material, and theta is equal to change in temperature. Calorimeter is based on the principle of conservation of energy. It states that heat lost by the hot bodies is equal to heat gained by the cold bodies. The essential requirement for calorimeter are: no heat escapes out from the calorimeter, no chemical reactions takes place between the different substances taken, change of state. Matter normally exists in 3 states: solid, liquid and gas. A transition from one of these states to another is called a change of state. Melting. The change of state from solid to liquid. Melting point. The temperature at which a solid and its liquid are in equilibrium at any fixed pressure. Vaporization. The change of state from liquid to vapor. Boiling point. The temperature at which the liquid and the vapor states of the substance coexist. Fusion. The change of state from liquid to solid. Regulation. Successive melting under pressure and freezing when pressure is relaxed at the surface at the interface of 2 blocks of ice. Sublimation. The process of transformation directly from the solid phase to the gaseous phase without passing through an intermediate liquid phase. Latent heat. The quantity of heat absorbed or released by a substance undergoing a change of state, such as ice changing to water at constant temperature and pressure. Heat transfer. Heat can be propagated in 3 ways. Number 1, by conduction. Number 2, by convection. Number 3, by radiation. Conduction. Heat transfer from one end of a solid substance to its other end without the actual movement of constituent particles. Convection. Heat is transferred from the higher temperature region to the lower temperature region due to the actual movement of constituent particles. Radiation. Heat is transferred from a body at high temperature to another body at lower temperature without having a direct contact between them. Thermal conductivity of a substance. The amount of heat transferred from the high temperature of a solid substance to the lower temperature is directly proportional to the area of cross-section of its faces. The temperature difference between 2 faces, time, and inversely proportional to the separation between the 2 faces. It gives Q is equal to Ka T1 minus T2 into T upon D, where K is a constant of proportionality and is called coefficient of thermal conductivity of the material of the substance. The coefficient of thermal conductivity of a substance may be defined as the amount of heat transferred from one phase of a unit cube of that substance to the opposite phase in unit time when these 2 phases are maintained at a unit temperature difference. Example. Let us take an example of thermal conductivity. Two rods A and B are of equal length. Each rod has the ends at temperature T1 and T2. What is the condition that will ensure equal rates of flow of heat through the rods A and B? Let's see the solution. Given L1 is equal to L2, since equal rates of flow of heat through the rods are being ensured, therefore delta Q1 upon delta T is equal to delta Q2 upon delta T. On solving the expression, we get A1 by A2 is equal to L1 by L2 into K2 by K1. Hence, A1 by A2 is equal to K2 by K1. Thus, the cross-sectional area of two rods must be in the inverse ratio of their thermal conductivity. Newton's law of cooling. It states that the rate of cooling of a body is directly proportional to the difference of the temperature of the body and the surrounding. The rate of cooling is directly proportional to T minus T naught. This law is valid when the temperature difference is not too large. Let's see the proof. Consider a body at a temperature T surrounded by a temperature T naught. Then the amount of heat energy emitted by the body per second is E is equal to sigma belongs to A T minus T naught into T plus T naught into T square plus T naught square. Since T is very close to T naught, it implies E is directly proportional to T minus T naught. Rate of cooling is directly proportional to T minus T naught. It proves Newton's law of cooling. Did you know? Calorimetry is the science associated with determining changes in energy of a system by measuring the heat exchanged with the surroundings. For an ideal gas, the volumetric thermal expansion depends on the type of process in which temperature is changed. Two known cases are isobaric change, when pressure is held constant, and adiabatic change, where no work is done and no change in entropy occurs. Newton's law of cooling is used to model the temperature change of an object of some temperature placed in an environment of a different temperature. Summary. Let us summarize what we have learned. A device used to measure the temperature of a body is called thermometer. Thermal expansion is defined as the process in which a substance expands on heating. Heat capacity of a body is defined as the amount of heat required to raise the temperature of the entire body by 1 degree Celsius. Calorimetry is based on the principle of conservation of energy, in which heat lost by the hot bodies is equal to the heat gained by the cold bodies. Transfer of heat by the collision among the molecules with their neighbor molecule is called conduction. Convection is the heat transfer mode in which the molecules move from place to place to transfer heat. Radiation is the fastest mode of heat transfer, which does not require any medium. Newton's law of cooling describes that the rate of loss of heat by a body is directly proportional to the difference in temperature with the surrounding.